The cosmos hides a faint vibration from the very beginning. These are the primordial ripples in space-time, the first tremors sent out during the universe's explosive birth. They are echoes of the Big Bang itself, and understanding them is the key to unlocking our cosmic origin story. By the end of this journey, you will have explored 30 mind-bending theories that attempt to explain these first whispers of creation. We will venture to the absolute limits of physics, where time itself may have broken down and reality was forged in a quantum fire. What do you think the universe sounded like when it was born? Our journey begins with the most established explanation, a theory known as cosmic inflation. Think of the newborn universe, not even a trillionth of a second old. Instead of a steady beginning, it underwent a growth spurt of unimaginable speed, inflating from a subatomic speck to a vast cosmic domain in a fleeting instant. This was not a gentle expansion, but a violent, exponential stretching of the fabric of space-time itself. During this frantic period, the empty vacuum of space was not truly empty. It was a seething quantum foam, where tiny particles and energy fluctuations would spontaneously pop in and out of existence. These are the quantum fluctuations, the microscopic jitters inherent to reality at its smallest scales. As the universe inflated at a rate faster than the speed of light, it did not simply get bigger. It stretched these infinitesimal quantum jitters along with it, magnifying them from the quantum world to the cosmic stage. What began as a tremor smaller than a single atom was stretched into a ripple light years across. These amplified fluctuations became the very seeds for all future structure in the cosmos. The denser patches would eventually, over billions of years, gravitationally collapse into the vast cosmic web of galaxies and galaxy clusters we see today. But crucially, this violent stretching also created a specific type of disturbance in the fabric of space-time itself, the primordial gravitational waves. The standard inflationary model makes a very precise prediction. It tells us that these first gravitational ripples should have left a unique, faint fingerprint on the oldest light in the universe, the cosmic microwave background. This fingerprint would manifest as a specific pattern of polarization, a subtle twisting in the direction of the light waves. Detecting this specific signal is one of the single most important goals in modern cosmology. It would be our most direct evidence that the universe really did undergo this incredible inflationary burst, confirming the quantum origin of everything we see. So the hunt for these first whispers is fundamentally a hunt for our own cosmic genesis, a search for the echo of inflation's thunderous roar. But what if the Big Bang was not the true beginning? Another theory proposes a far more ancient and cyclical origin, an event known as the ekpyrotic universe. This idea completely reimagines our cosmic genesis. It suggests our universe exists as a three-dimensional membrane, or brain, floating within a higher dimensional space. Picture our entire cosmos as a single, vast sheet of reality. Now imagine another cosmic sheet, a parallel universe, floating nearby in this hidden dimensionality. According to the ekpyrotic model, our Big Bang was not a moment of creation from nothing. It was the result of a cataclysmic collision between our brain and this other parallel universe. This was not a gentle meeting, but a violent, direct impact that injected immense energy and set our expansion into motion. This collision would have also generated its own unique set of primordial ripples in space-time. However, the gravitational waves produced by such a brain collision are predicted to be fundamentally different from those of inflation. The process is far less turbulent, resulting in a much quieter, more subdued spectrum of waves. The telltale fingerprint they would leave on the cosmic microwave background would be far weaker and in a different pattern, making them a much more elusive target for our telescopes. This theory challenges one of our most fundamental assumptions. It suggests that the Big Bang was not a singular starting point, but merely one chapter in an endless cosmic cycle. In this view, the universe may have no true beginning and no final end, only an eternal rhythm of collisions, expansions, and contractions. A great bounce echoing through eternity. Yet another possibility emerges from the deepest layers of theoretical physics, a vision where the universe's fundamental building blocks are not particles, but tiny, vibrating strings. This is string gas cosmology. It reimagines the very first moments not as a rapid inflation, but as a hot, dense, and static gas. Picture a cosmos filled with a seething ocean of these fundamental strings, all vibrating and interacting with one another in a confined toroidal space. Their endless dance, their specific resonant frequencies, are what ultimately generate the structure of our reality. The gravitational waves born from this chaotic string gas would carry a distinct and dramatic signature. Unlike the gentle, random pattern predicted by inflation, the ripples from this stringy origin would be intensely non-Gaussian. This is a complex term for a simple idea. It means the waves would not be a uniform sea of random humps. Instead, they would contain sharp, correlated features, like specific harmonies in a cosmic symphony or distinct clumps in the fabric of space-time itself. This non-Gaussian fingerprint would be a dead giveaway, a clear signal that our universe began not with a sudden stretch, but from the intricate vibrations of strings. Detecting such a pattern would force us to rewrite our cosmic history, pointing to an origin woven from the deepest vibrations of reality itself. How different would our universe look if its first whispers were not a roar, but a complex melody? The universe may have changed state in its fiery youth, much like water crystallizing into ice. This theory of cosmological phase transitions suggests a cosmos undergoing sudden, violent shifts. In its earliest, hottest moments, the fundamental forces of nature were likely unified into a single, supreme force. As the universe expanded and cooled, it crossed a critical threshold. This triggered a phase transition, a moment where the unified force fractured into the distinct forces we recognize today, the electromagnetic and the weak nuclear force. This event, known as the electroweak phase transition, was not a gentle process. Think of a pot of water on the verge of boiling. Bubbles of a new phase, a new state of reality, would have spontaneously formed in the seething cosmic broth. These bubbles of a lower energy vacuum began to expand at nearly the speed of light, their walls racing outward. Where these violently expanding bubbles eventually collided and merged, they would have released titanic bursts of energy. The collisions were so immense, so catastrophic, that they literally shook the foundations of reality. Each impact would have sent powerful, ringing vibrations through the fabric of space-time itself, generating a distinct spectrum of primordial gravitational waves. Unlike the smooth hum predicted by inflation, these ripples would carry the signature of a turbulent, bubbling cosmos. They would tell a story of a universe not just stretching, but of reality itself restructuring, breaking its own symmetry in a moment of cosmic upheaval. What would it mean to hear the echoes of these ancient, colliding bubbles? It would be the sound of the universe settling into its fundamental laws, a snapshot of the very moment the forces that govern our reality were born. Perhaps the first ripples in space-time came not from a stretching cosmos, but from the birth cries of its very first monsters, A population of tiny, primordial black holes could have formed in that chaotic first second, not from dying stars, but from the direct collapse of regions so dense they pinched off into their own pockets of reality. Think of the universe in its infancy as a pot of violently boiling water, with bubbles of vastly different densities constantly forming and popping. In this theory, the densest of these bubbles did not pop. Instead, their own immense gravity caused them to catastrophically collapse, each one becoming a microscopic black hole. The formation of each one of these holes would have been a singularly violent event, a sudden and traumatic puncture in the fabric of space-time that sent a powerful shockwave of gravitational energy rippling outward. This was not a gentle hum, but a sharp, staccato burst of ripples. And the story does not end with their birth. These primordial black holes would then drift through the cosmos, sometimes finding one another. When two of them merged, their final spiraling dance would have unleashed another crescendo of gravitational waves, adding to the cosmic chorus. Even their deaths, through a process known as Hawking radiation where they slowly evaporate, could have left a faint, high-frequency whisper in the background. So the signal we are searching for might not be a smooth echo from inflation, but a cacophony of pops and chirps from the universe's first and most mysterious inhabitants. What if the oldest thing we can detect is the fading tremor from a black hole that lived and died in the first instant of time? Another kind of cosmic filament could have woven the first ripples directly into the fabric of space-time. These are cosmic strings, theoretical scars left over from the universe's earliest phase transitions. As the cosmos cooled and its fundamental forces separated, the fabric of reality may not have settled evenly. Think of it like the formation of cracks in ice, or the tangled threads that appear when you rapidly pull apart two pieces of Velcro. Cosmic strings are those cracks, one-dimensional defects of pure energy, impossibly thin yet denser than anything we can conceive. A single string just a mile long would possess more mass than our entire planet. These are not strings in the sense of violin strings, but more like ultra-dense, spaghetti-like filaments stretching across the cosmos, some perhaps as long as the universe itself is wide. And they are not static. They would have been born vibrating, whipping through the cosmos at nearly the speed of light. Their oscillations, their intersections, and the formation of closed loops when they cross and reconnect would be events of unimaginable energy. Every whip-crack motion, every time a loop pinches off and begins to oscillate, it shakes the very foundation of reality. These vibrations do not travel through space-time. They are vibrations of space-time itself, continuously pumping gravitational waves out into the universe. This would not be a single echo from a long-past event. It would be a persistent, undying hum, a background choir of space-time ripples generated throughout cosmic history. The signature of this hum would be utterly unique. Unlike the broad spectrum of waves from inflation, cosmic strings would produce a very specific, sharp spectrum of frequencies, a clear harmonic signature etched into the cosmos. Listening for this specific hum is like trying to pick out a single, pure note from a cacophony of noise. Finding it would reveal a universe crisscrossed by the ancient, vibrating scars of its own violent birth, a cosmic tapestry still ringing from its creation. Perhaps inflation was not the cold, empty process we once thought. A theory called warm inflation proposes a radically different environment for the universe's great expansion. In this version, the inflating universe was not a near vacuum. It was a hot, dense, and interactive plasma, filled with a constant bath of newly created particles. Think of it as expanding through a thick, cosmic syrup rather than through empty space. This constant friction, This interaction with the particle bath would have dramatically changed the nature of the quantum fluctuations. The process would have dampened the most powerful vibrations, suppressing the violent stretching that creates the strongest gravitational waves. The resulting signal would be a much quieter whisper, a faint hum that our current experiments might struggle to hear. This is a crucial twist in our hunt. We are not just looking for one specific signal, we must also listen for the profound silence that a theory like this predicts. The absence of a loud, clear signal could itself be a message, telling us that the universe's birth was a warmer, more crowded event than the standard story allows. Then there are the truly exotic possibilities, theories that rewrite the rules of gravity itself. One such idea is known as ghost condensation. This is not a modification of the matter in the universe, but a change to the very stage upon which the cosmic drama plays out. It introduces a new, fundamental field that alters how space-time behaves at the most extreme energies. In some versions of this theory, this new field can act like a cosmic amplifier, taking the tiny quantum jitters and boosting them into a deafening roar of gravitational waves. The primordial ripples would be far stronger and potentially at a much higher frequency than anything standard inflation predicts. In other scenarios, this new physics could have the opposite effect, placing a cosmic damper on the vibrations and suppressing the waves into near silence. The key point is that these alternative fields create a spectrum of possibilities far wider than the single, clear prediction of the simplest models. Our search for the first ripples is therefore also a direct test of gravity's own nature in that first fleeting instant. Finding a signal that is too loud or too quiet, or of the wrong pitch, would be just as revolutionary as finding the signal itself. It would force us to admit that Einstein's theory, as magnificent as it is, was only part of the story, and that the true laws of creation are even stranger than we dream. What if gravity itself was different when the universe was born? The search for these first ripples might do more than reveal our own universe's birth. It could open a window into the cosmic beyond. Imagine our cosmos not as the entirety of existence, but as a single bubble of stable space, floating in an infinite, eternally inflating sea. This is the theory of eternal inflation, a multiverse on the grandest possible scale. In this endless expanse, new universe bubbles are constantly nucleating, popping into existence with their own unique laws of physics, each one a separate cosmic experiment. Our entire observable universe is just one of these bubbles. The moment of our own Big Bang was simply when our particular bubble of space stopped inflating and began the slower, more familiar expansion we live in today. But in that chaotic foam of eternally inflating space, these bubbles do not always form in isolation. Sometimes, in the first instance of a bubble's life, it can collide with a neighboring universe. The impact would have been a cataclysmic event, a direct meeting of two separate realities. Such a collision would have sent a tremendous shockwave reverberating through the very fabric of our young cosmos. This would not create a uniform hum, but a distinct directional imprint, an anisotropy. It could appear as a specific, strange pattern in the gravitational wave background, a kind of cosmic bruise. Or it might manifest as a giant cold spot in the cosmic microwave background, a vast region of space that is inexplicably cooler than the rest, a scar from a long ago encounter with another universe. Detecting such a signature would be the first tangible evidence that we are part of a much vaster multiverse. The primordial ripples we are trying to hear may not just be the echo of our own beginning, but the fading tremor from a collision with another reality entirely. What would it mean to find the fingerprint of another cosmos imprinted on our own? Our search for a beginning might be looking in the wrong place entirely. Before the hot, dense state of the Big Bang, the cosmos could have existed in a timeless, static phase. This is the emergent universe scenario. Picture a universe that was always here, not expanding or contracting, but simply persisting in a quiet, steady state for an eternity. In this view, there is no true moment of creation, no initial singularity where the laws of physics break down. Instead, the universe underwent a gentle, smooth transition from this eternal static state into the expanding cosmos we recognize. That transition point is what we now call the Big Bang. The shift itself, this cosmic awakening, would have been a profound event. As the universe stirred from its slumber and began to stretch, the quantum fluctuations present in that prior state would have been gently amplified. They were stretched into the seeds of structure and, simultaneously, generated a faint, unique spectrum of primordial gravitational waves. The ripples from this model would be distinct, potentially quieter, and with a different character than those from a violent inflationary burst. They would be the echoes not of a beginning, but of a great awakening, a universe shifting gears from stillness into motion. This idea elegantly sidesteps the philosophical puzzle of a true beginning, suggesting our cosmos is not a one-time event, but an entity that simply changed its state. Another theory takes this idea of a prior existence and gives it a dramatic, cyclical twist. Loop quantum cosmology applies the rules of quantum gravity to the entire universe, and it paints a stunning picture. It suggests that before our expansion, there was a great cosmic contraction. A previous universe, perhaps very much like our own, reached the end of its life and began to collapse under its own gravity. But according to this theory, it did not crush itself into an infinitely dense singularity. Instead, the repulsive force of quantum gravity became so powerful that it stopped the collapse and triggered a rebound. This was the big bounce. The moment of the bounce itself would have been one of the most violent events conceivable. The entire mass and energy of a previous cosmos, rebounding in a single instant, would have shaken the fabric of reality to its core. This tremendous jolt would have generated an incredibly powerful blast of primordial gravitational waves, a ringing echo of the bounce that would permeate the new universe. The signature of these waves would be a clear, sharp signal, a direct fossil of that cosmic rebound. Finding it would be evidence that our universe was born not from nothing, but from the death of another, in an endless, majestic cycle of cosmic renewal. What if the first whisper we are trying to hear is actually the last gasp of a universe that came before our own? The search for the first ripples now leads us to a ghost. Deep within the mathematics of particle physics lies a hypothetical particle known as the action, a whisper-light entity that is one of the leading candidates for the universe's missing dark matter. But its potential role may reach back even further, to the very first moment of cosmic inflation. In certain models, it is not a generic energy field that drives the universe's explosive growth, but a field governed by this specific action. This action-driven inflation works in a unique way, rolling and oscillating in a manner that imprints its own distinct signature on the fabric of space-time. The primordial gravitational waves generated by this process would not be a random sea of vibrations. They would be chiral. Chirality is a concept of handedness, like a pair of gloves. Your left and right hands are mirror images, but you cannot simply rotate one to match the other. In the same way, gravitational waves can theoretically spin in either a left-handed or right-handed direction as they travel through the cosmos. Most theories predict an equal mix of both, But an action-driven universe would break this symmetry. It would produce a gravitational wave background with a clear preference, a dominant handedness. This would be a smoking gun signature, a clear fingerprint that could not be easily explained by any other process. Detecting this chiral background would be like finding that every single ripple in a pond spiraled only clockwise. It would point directly to the action, linking the mechanism of inflation to the mysterious dark matter that shapes our cosmos today. The first tremors of space-time could carry a spin that reveals the identity of one of the universe's most elusive ghosts. The very substance that filled the infant cosmos might have been far stranger than we can conceive. Among the most exotic proposals are fields known as K-essence. Unlike the simple energy fields of standard inflation, K-essence fields possess a non-standard dynamic kinetic energy. Think of it like this. A normal field is like a ball rolling slowly down a gentle hill. A K-essence field is like that same ball suddenly encountering a stretch of bizarre physics, where its speed and momentum interact in unnatural ways, sometimes making it accelerate wildly or slow to an impossible crawl. This strange behavior directly impacts how the field jitters and fluctuates. The quantum vibrations that get stretched into gravitational waves can be dramatically suppressed or wildly amplified depending on the specific nature of this kinetic energy. The resulting primordial ripples could be a faint, almost silent hum, or they could be a deafening roar, a signal so strong it would be impossible to miss. Our search is not just for a whisper, but for the entire range of volumes that such exotic physics could produce. Another candidate for the universe's primordial content is the Chaplain gas. This is a theoretical substance that offers a stunning unification. It behaves like dark matter in the early universe, clumping together to form the seeds of galaxies, but then it smoothly transitions to behave like dark energy in the later cosmos, driving the accelerated expansion we see today. One single, mysterious component would be responsible for both the structure and the ultimate fate of everything. If such a fluid filled the cosmos during its first moments, it would have left a distinct mark on the gravitational wave background. The transition of this gas from a clumping material to a smooth, repulsive force would have imprinted a specific signature on the spectrum of the waves. Detecting this signature would be a monumental discovery, revealing that the two greatest mysteries of the cosmos, dark matter and dark energy, are not separate entities at all, but two faces of the same fundamental substance. The first ripples would then be a direct message about the true, unified nature of the cosmos's dominant components. Then there is the most terrifying possibility of all, phantom energy. This is a hypothetical form of dark energy with a truly bizarre property. It possesses negative kinetic energy. If phantom energy is real, it would cause the expansion of the universe to accelerate not just steadily, but at an ever-increasing rate that grows without bound. The ultimate fate in this scenario is not a slow fade, but a catastrophic big rip. Billions of years from now, the repulsive force would become so strong that it would first tear apart galaxy clusters, then galaxies, then solar systems, and finally, it would rip apart atoms and the very fabric of space-time itself. Now, consider the implications for the beginning. If the infant universe was ever dominated by a form of this phantom energy, even briefly, its violently repulsive nature would have shaken space-time with incredible force. The gravitational waves generated during such a phase would be immense, carrying a unique, sharp signature of that ancient destructive power. The first whispers we are trying to hear could be the faint, leftover tremor from a force that still lurks in the vacuum, waiting to one day tear our reality apart at the seams. Reality itself may be a projection, a cosmic illusion. The holographic principle suggests that our three-dimensional universe, with all its stars, galaxies, and emptiness, could be information encoded on a distant, two-dimensional surface. Everything we see and feel, including the force of gravity, might be a hologram projected from this fundamental boundary. This is not science fiction, but a serious consequence of uniting quantum mechanics with our understanding of black holes. If true, it means there is a fundamental limit to the amount of information, the number of bits, that can be stored in any given volume of space. The cosmos has a maximum resolution, a pixel size. This profound limit would have left its mark on the universe's first moments. During the violent processes that generated the primordial ripples, the holographic limit would have acted as a cosmic damper. It would have suppressed the creation of gravitational waves with incredibly small wavelengths, the highest frequency vibrations. These are the ripples that would have shaken space-time on the tiniest of scales, smaller than the universe's inherent pixel size. The principle forbids such fine-grained detail. The result would be a distinct and telling feature in the spectrum of gravitational waves we hope to observe. Instead of a continuous hum across all frequencies, there would be a sharp cutoff, a sudden silence at the high-frequency end. It would be as if you were listening to a symphony and every note above a certain pitch simply vanished from existence. Finding this specific cutoff in the gravitational wave background would be staggering evidence that we are living inside a hologram, that the three-dimensional richness of our reality is a magnificent shadow cast by a simpler, lower-dimensional truth. The first whispers of the universe would carry the signature of its own illusory nature. Supersymmetry proposes a profound and elegant symmetry woven into the fabric of reality itself. For every known particle we have discovered, from electrons to quarks, there should exist a superpartner, a hidden twin with different quantum properties. This doubling of the cosmic particle roster is not just a theoretical curiosity, it is a potential key to understanding the very first moments. During the inflationary epoch, when the universe was a seething quantum foam, these superpartners would have been present and active. Their existence opens up entirely new channels for interaction and energy transfer. Instead of just one type of quantum jitter being stretched into gravitational waves, the complex dance between particles and their superpartners could have dramatically amplified the process. The production of primordial ripples would have been supercharged, creating a gravitational wave signal far stronger and more pronounced than the simplest models of inflation predict. We could be searching for an echo that is much louder than we anticipated, a direct consequence of this hidden cosmic symmetry. But to make this symmetry truly fundamental, we must go a step further. Supersymmetry becomes local in the framework of supergravity. This theory merges supersymmetry with Einstein's general relativity, creating a more complete picture of how space-time behaves at these incredible energies. Supergravity dictates how the inflationary field itself must interact with gravity and its own superpartners. This interaction shapes the inflationary potential, the metaphorical landscape that the field rolled down to drive the universe's expansion. Different formulations of supergravity create uniquely shaped potentials, some with steeper cliffs and more dramatic plateaus than others. The precise shape of this potential dictates everything about the quantum fluctuations and, consequently, the gravitational waves produced. Therefore, the specific fingerprint of the first ripples, their amplitude and their spectrum across different frequencies, becomes a direct test of which supergravity model, if any, correctly describes the birth of our universe. The faint hum we are trying to detect could carry the signature of a reality where every particle we know has a hidden twin, and where gravity is united with this supreme symmetry. Stephen Hawking and James Hartle proposed a universe with no boundary in time, a cosmos without a definitive starting gun. Their no-boundary proposal is a profound application of quantum mechanics to the entirety of existence. It suggests that if we could rewind the cosmic clock back toward the moment of the Big Bang, time itself would lose its familiar meaning. It would smoothly transform, becoming more like a dimension of space. In this quantum genesis, there is no singular point of infinite density, no sharp edge where the universe begins. Instead, the cosmos is a self-contained, finite entity without a beginning, much like the surface of the Earth is finite yet has no edge you can fall off. This elegant idea has a direct and testable consequence for the first ripples in space-time. The no-boundary wave function of the universe does not allow for just any initial conditions. It selects for the smoothest, most regular possible start. This profound preference for smoothness means the quantum jitters that get stretched into gravitational waves are inherently suppressed. The violent, chaotic vibrations that other theories rely on are simply not present in this model. The resulting spectrum of primordial gravitational waves would be exceptionally quiet, a whisper so faint it might be nearly impossible to detect with our current technology. Therefore, the ongoing hunt for these waves becomes a direct test of this quantum origin story. If we were to detect a loud, clear signal of primordial gravitational waves, it would pose a serious challenge to the no-boundary proposal. Its prediction of a suppressed signal is a bold and specific claim. The silence of our detectors, the failure to find those first tremors, could paradoxically be the most compelling evidence that Hawking and Hartle were right, that our universe simply smoothed into existence from a timeless quantum blur. The matter you are made of is a cosmic anomaly. For every particle of matter created in the Big Bang, an equal amount of antimatter should have been born. Yet when matter and antimatter meet, they annihilate in a flash of pure energy. If the universe had been perfectly balanced, everything would have vanished in a great flash of mutual destruction, leaving behind a sea of radiation and nothing more. The simple fact that we exist, that stars and galaxies fill the cosmos, is proof that a fundamental rule was broken. Somehow, for every billion pairs of matter and antimatter that annihilated, a single solitary particle of matter was left behind. This is the mystery of baryogenesis, the genesis of matter's dominance. The very processes that created this imbalance may have violently shaken the fabric of space-time, leaving behind ripples we can still search for today. One leading theory, electroweak baryogenesis, places this pivotal moment during the electroweak phase transition we encountered earlier. But for it to create the matter asymmetry we see, this transition could not have been smooth and gentle. It had to be a first-order phase transition, a violent, bubbling process. As the universe cooled, bubbles of the new, broken symmetry phase would have nucleated and expanded at nearly light speed. Crucially, the walls of these expanding bubbles would have created the conditions to preferentially produce matter over antimatter. It is within these raging, ultra-fast walls that the symmetry between matter and antimatter was permanently broken. And when these bubbles, each carrying the seed of our material existence, collided and merged, the energy released would have been staggering. These colossal impacts would have sent powerful, ringing gravitational waves cascading through the young cosmos. The gravitational wave background from such an event would be a direct echo of the process that made our existence possible. Another compelling idea is leptogenesis. This theory suggests the matter-antimatter imbalance originated not with quarks, but with neutrinos, extremely heavy, sterile neutrinos, existing only in the earliest moments, would have decayed asymmetrically, producing slightly more ordinary matter particles than antimatter. This initial lepton asymmetry was then converted through subtle particle interactions into the baryon asymmetry we see today. While the mechanism is different, the gravitational wave signature can be strikingly similar. The scale of these processes often requires another, earlier phase transition, a separate bubbling of the cosmic vacuum that provided the energy and conditions for those heavy neutrinos to do their work. That phase transition, occurring at a tremendous energy scale, would have also generated its own powerful burst of gravitational radiation. So the hunt for these specific space-time ripples is not just a search for our origin, but a direct test for the answer to a profound question. Why is there something rather than nothing? The faint hum we are trying to detect could be the literal vibration from the moment the universe decided to favor matter, the tremor from the event that allowed every atom in your body to eventually come into being. Some particles are born to break the rules. Tachyons are purely hypothetical entities that do not simply move faster than light. They are forced to, existing in a state where their rest mass is an imaginary number, a mathematical absurdity that defies our everyday logic. While never observed, their theoretical possibility opens a door to one of the most explosive origins for the universe's first whispers. Imagine the infant cosmos as a field of pure potential, a state known as a scalar field. In a tachyon-driven model, this field was initially in a state of unstable equilibrium, like a pencil perfectly balanced on its tip. It was a false vacuum, a precarious configuration destined for a sudden and dramatic collapse. The moment this field underwent tachyonic condensation was the moment it lost its stability, tipping over into a true lower energy state. This was not a gentle roll downhill. It was an instantaneous, violent phase transition that swept across the entire universe faster than light could travel. The energy released in this catastrophic event was immense, shaking the very foundations of space-time with unprecedented force. This process would have been an extraordinarily efficient generator of primordial gravitational waves. The sheer speed and violence of the condensation would have pumped a massive amount of energy directly into the fabric of reality, creating a powerful, ringing echo. But the true signature of this event lies in its frequency profile. The specific dynamics of a tachyonic instability produce a gravitational wave spectrum that is sharply peaked. Instead of a broad hum across many frequencies, the signal would be dominated by a specific, characteristic frequency, a single resonant note in the cosmic symphony. Detecting such a sharp, powerful peak in the gravitational wave background would be a clear fingerprint of this tachyonic birth. It would suggest that our universe began not with a smooth expansion, but with a sudden, rule-breaking collapse of an unstable field, a cosmic shiver that set the stage for everything to come. Beyond the smooth continuum of space-time lies a reality built from discrete grains. Causal set theory proposes that the fabric of our universe is not a continuous sheet, but a vast collection of fundamental, indivisible events. Think of it as a cosmic tapestry woven from individual, microscopic points, each one connected to others in a specific order of cause and effect. This is not just a different picture of reality, it is a fundamentally new one, where the smooth geometry we experience is merely an emergent illusion, a blurry average of an underlying granularity. At the tiniest possible scale, the Planck scale, this granular structure would have directly influenced the birth of the first gravitational waves. When the universe was young and incredibly dense, these fundamental grains of space-time were all there was. The process that generated the primordial ripples would have been a quantum dance playing out on this discrete stage. The granularity would have acted like a cosmic filter, subtly suppressing the creation of gravitational waves with wavelengths so small they could resolve the individual grains themselves. This would leave a distinct, telltale signature in the gravitational wave background we hope to observe. Instead of a smooth spectrum of ripples across all frequencies, there would be a faint, rolling dampening at the very highest frequencies, a subtle silence imposed by the pixelated nature of reality. Detecting this signature would be like discovering that the universe has a maximum resolution, confirming that space and time themselves are not smooth and infinite, but are composed of a finite number of fundamental elements. The first ripples would carry the faint echo of this cosmic pixelation. Another theory takes this idea of a fundamental structure even further, proposing that space-time is not just granular, but fundamentally fuzzy. Non-commutative geometry suggests that at the Planck scale, the very coordinates of space-time cease to commute. What does that mean? In our everyday world, it does not matter if you measure an object's position first, and then its momentum, or the other way around. The order of operations does not change the result. But in the furious quantum foam of the early universe, non-commutative geometry posits that this was not true. The sequence in which you measured location and direction would have yielded different outcomes, creating a fundamental uncertainty woven into the geometry of space itself. This fuzziness would have profound consequences for the first gravitational waves. As these ripples propagated through this fuzzy, non-commutative background, their journey would not have been clean. The fuzzy structure of space-time would have subtly scrambled the waves, affecting both their propagation speed and, most importantly, their polarization. The delicate twisting pattern of the gravitational waves, the very fingerprint we use to identify their origin, would be modified. A clear chiral signal might become muddled, or a uniform pattern could develop unexpected correlations. Finding such a modification in the polarization of the primordial gravitational wave background would be direct evidence that the stage of reality itself was once a blurred and uncertain place, where the classical rules of geometry had not yet solidified. These two theories represent the absolute frontier of our quest. They ask us to consider that the first whispers of the universe are not just a message from the past, but a direct signal from the fundamental building blocks of reality, a tremor that passed through a world of discrete grains and fuzzy coordinates long before the smooth cosmos we know even existed. These profound theories demand an equally profound search, a hunt for whispers across the cosmos. Our primary tools in this quest are monumental feats of engineering known as laser interferometers. Imagine two identical, perfectly straight tunnels, each 4 kilometers long, arranged in a giant L shape. A single laser beam is split, sending a beam down each arm to bounce off a mirror and return. In perfect stillness, when no gravitational wave passes, the returning light waves cancel each other out through a process called destructive interference. But when a ripple in space-time washes over the Earth, it does something almost imperceptible. It stretches one arm of the detector by an infinitesimal amount while squeezing the other. This tiny change, smaller than 1/10,000th the width of a proton, alters the distance the laser light travels just enough to disrupt the perfect cancellation. The light waves no longer line up, and a flicker of light, a signal, is born. This is the exquisite principle behind observatories like LIGO in the United States and Virgo in Italy, listening posts designed to feel the vibrations of the universe itself. Their current sensitivity is staggering, capable of detecting relative length changes of 1 part in 1,000 billion billion. That is like measuring the distance to our nearest star, Proxima Centauri, with an accuracy less than the width of a human hair. These instruments are tuned to listen for the most violent events in the modern universe, the collisions of black holes and neutron stars. These cataclysms create gravitational waves in a specific frequency range, roughly between tens and thousands of hertz, a bass note in the cosmic symphony. Yet, this very focus presents our greatest challenge. The primordial gravitational wave background from the Big Bang is a constant random hum, a static hiss that permeates all of space. It is not the sharp chirp of a black hole merger. To find it, we must sift this ancient static from the louder, more distinct signals of these later cosmic crashes, like trying to hear the faint, steady sound of rainfall while standing next to a series of exploding fireworks. The hunt requires not just incredible machines, but incredible patience and new ways of listening. But to hear the universe's first whisper, we must escape the noise of our own world. The future of this search lies not on Earth, but in the serene quiet of space, with a mission known as LISA, the Laser Interferometer Space Antenna. Picture 3 identical spacecraft, flying in a perfect triangular formation, with each side of the triangle measuring 2.5 million kilometers long. That is a distance roughly 6 times farther than the Moon is from Earth. These 3 satellites will form the arms of the most sensitive measuring device ever conceived, a laser interferometer of truly cosmic proportions. While ground-based detectors like LIGO listen for the high-frequency chirps of stellar collisions, LISA is designed to hear the deep, low-frequency hum that fills the cosmos. It is tuned to an entirely different part of the gravitational wave spectrum, the domain where the oldest and most persistent signals reside. This low-frequency band is where the stochastic gravitational wave background from the early universe is predicted to be strongest. It is a constant random hiss, the combined roar of every inflationary model, every cosmic string vibration, and every phase transition from the first moments of time, all overlapping into a single pervasive hum. LISA's incredible sensitivity to these low frequencies makes it the prime instrument capable of sifting this ancient static from the silence. Its successful launch and operation would open a direct auditory channel to the birth of the cosmos, allowing us to listen to the vibrations of processes we can only theorize about today. The data it collects will not be a single clear note, but a rich spectrum of sound. The shape of that spectrum, its amplitude and its tilt across different frequencies, will be our most powerful tool for discriminating between the 30 theories we have explored. A loud, clear signal at these low frequencies could be a smoking gun for cosmic strings, their persistent oscillations still ringing through the void. A specific chiral spin in the waves would point directly to an action-driven inflation. A spectrum with a sharp cutoff at high frequencies could be the telltale sign of a holographic universe. Conversely, if LISA hears only profound silence where we expect a roar, it could rule out entire classes of models, perhaps pointing us toward a no-boundary quantum origin or a warm, dampened inflation. This is not just another telescope. It is a time machine for our ears, an instrument that will finally test our grandest ideas about creation itself. The first tremors of reality have been traveling for over 13 billion years. Soon, we will have a receiver quiet enough and vast enough to finally listen. While our grandest space-based detectors are still on the drawing board, another path to the first whispers has been quietly yielding clues for decades. This search focuses on the oldest light in the universe, the cosmic microwave background. This faint glow is the remnant heat from the Big Bang, a snapshot of the cosmos when it was just 380,000 years old. Before that moment, the universe was a hot, opaque plasma, too dense for light to travel freely. As it expanded and cooled, it finally became transparent, and that first burst of light has been traveling ever since, carrying an imprint of the universe in its infancy. It is on this ancient canvas that primordial gravitational waves would have left their most enduring mark. As these space-time ripples propagated through the early universe, they literally squeezed and stretched the fabric of reality, which in turn compressed and rarefied the hot plasma. This created a specific twisting pattern in the direction, or polarization, of the CMB light. This unique signature is known as B-mode polarization. Think of it like the surface of a pond. If you simply push the water straight down, you create a radial pattern. But if you give the water a slight twist as you push, you create a curling, vortex-like effect. Primordial gravitational waves are that cosmic twist, imparting a distinct curl to the polarization of the ancient light. Finding this specific B-mode pattern is the holy grail for many cosmologists, as it would be a direct, fossilized imprint of those first tremors. The hunt for this signal is led by incredibly sensitive telescopes stationed in the most extreme environments on Earth, like the high, dry plateaus of the South Pole. Experiments like the BICEP and Keck array have spent years staring at a single, ultra-clean patch of sky, searching for this faint curl in the CMB. The challenge is monumental, as the signal they seek is incredibly subtle, easily drowned out by a far more local source, interstellar dust within our own Milky Way galaxy. This dust, when aligned by magnetic fields, can also polarize light and produce its own B-mode patterns, creating a foreground fog that obscures the ancient cosmological signal. Separating the cosmic twist from the dusty mimic requires immense precision and data from multiple sources, including the all-sky maps from the Planck satellite. The next generation of observatories, like the Simons Observatory now being built in Chile's Atacama Desert, will deploy an army of thousands of detectors with unprecedented sensitivity. Their goal is to measure the polarization of the CMB with such fine detail that they can definitively peel back the veil of galactic dust and listen for the faint, curling whisper of the universe's birth. This is a painstaking, meticulous process, a forensic analysis of the oldest crimes seen in existence, searching for the one piece of evidence that could tell us how it all began. A galactic clock ticks with unimaginable precision, its rhythm written in the silent depths of space. These are pulsars, the spinning corpses of massive stars, beaming out radiation with a regularity that rivals our most advanced atomic clocks. They are the universe's natural lighthouses, and their unwavering pulses are now being used to construct the largest scientific instrument ever conceived, a detector spanning the entire Milky Way. This is the principle behind a pulsar timing array. When a gravitational wave, a ripple in the fabric of space-time, passes through our galaxy, it does something extraordinary. It minutely stretches and compresses the space between the Earth and these distant pulsars. The effect is almost vanishingly small, a change in the timing of the pulses by mere billionths of a second. But by meticulously monitoring an entire network of these cosmic clocks, dozens of them scattered across the sky, scientists can detect a correlated drift in their rhythm. As a gravitational wave washes over the galaxy, it will make the pulses from one set of pulsars arrive slightly early, while pulses from another direction arrive slightly late, creating a unique, correlated pattern across the array. Collaborations like NanoGrav in North America have been collecting this data for over 15 years, listening for a faint, persistent hum in the nanohertz frequency range. This is a part of the gravitational spectrum utterly inaccessible to ground-based interferometers like LIGO. It is an incredibly low base note, with a single wave cycle taking years to pass by. The primary source expected to create this hum is the combined rumble of countless pairs of supermassive black holes, orbiting each other in the hearts of distant galaxies, their colossal dance shaking the cosmos. Yet there is a more profound possibility shimmering at the edge of detection. This same method, this galactic-scale ear, could potentially sense the gravitational wave background from the universe's birth. The same primordial ripples that might have imprinted the cosmic microwave background would also create a stochastic hum in this nanohertz band, disentangling the ancient birth cry from the modern chorus of black holes is the monumental challenge. The signature of the primordial background would have a distinctive spectrum, a specific tilt across the frequencies that differs from the signal produced by black hole binaries. Finding that specific fingerprint within the hum would be like identifying the voice of a single singer within a vast cosmic choir, a whisper from the first moments of time heard through the ticking of dead stars. Detecting a signal is only the very beginning of the challenge. The true puzzle lies in interpretation, in understanding exactly what the cosmos is trying to tell us. Each of the 30 theories we have explored makes a distinct prediction for the character of these first ripples. The amplitude of the waves, their spectrum across different frequencies, their unique polarization, and their statistical texture, all of these properties combine to form a kind of cosmic barcode. A smooth, quiet hum points toward a warm, dampened inflation or a no-boundary quantum origin. A loud, roaring signal, especially with a specific spin, screams of action fields or dramatic modifications to gravity itself. A sharp, clumpy, non-Gaussian pattern is the hallmark of a string gas origin, while a persistent harmonic hum across frequencies is the undeniable signature of cosmic strings. This is the grand inverse problem of cosmology. We are handed a single, complex signal, a single barcode scan from the beginning of time, and our monumental task is to run it through a library of every possible Genesis story to find the one match. It is a forensic analysis on a cosmic scale. The first confirmed detection will not be an endpoint, but a starting gun for a new era of theoretical debate. It will rule out vast families of theories in an instant, while elevating a handful of contenders to the forefront of science. The faint tremor we finally detect will not simply tell us that the universe shook. It will tell us how it shook, and in that how, we will find the answer to why we are here at all. The most profound discovery might be a universal silence. What if, after decades of searching with ever more sensitive instruments, we find nothing? No faint hum in the pulsar timing arrays, no curling pattern in the cosmic microwave background, no low-frequency rumble from space-based interferometers. This apparent failure would not be an end to the quest, but a revolution in disguise. The absence of a signal is itself a powerful signal, one that would force us to tear up the most cherished pages of our cosmic origin story. A persistent non-detection would deliver a devastating blow to the simplest and most popular models of cosmic inflation. These theories, which form the bedrock of modern cosmology, predict a clear, detectable whisper of primordial gravitational waves. If our most advanced ears hear only silence, it means our basic understanding of the universe's explosive birth is fundamentally flawed. This great quiet would be a directive to explore the roads not taken, the theories that have always predicted a much weaker signal. It would provide compelling evidence for the ekpyrotic universe, where our Big Bang was a quiet collision of brains rather than a thunderous inflationary burst. That silent, cyclical origin would suddenly become a leading contender. The profound hush would also sing the praises of the no-boundary proposal, Stephen Hawking's vision of a universe that simply smoothed into existence from a timeless quantum state. Its inherent preference for smoothness leaving behind only the faintest of tremors. A silent universe would be a universe that began not with a bang, but with a whisper so soft we can scarcely conceive of it, forcing a total and breathtaking rethink of our entire cosmic paradigm. These first ripples are more than just ancient echoes. They are a direct message from the only era where gravity itself was quantum. For a fleeting moment at the very beginning, the entire observable universe was compressed into a volume so tiny that the rules of the quantum world, which govern particles, were inseparable from the rules of gravity, which govern the cosmos. This is the domain of quantum gravity, the single greatest unsolved problem in all of physics. Einstein's theory of general relativity beautifully describes gravity as the curvature of space-time, but it is a classical theory. It breaks down completely at the immense densities of the Big Bang, where quantum fluctuations would have been shaking the very fabric of reality. Our current understanding simply cannot describe a reality where space-time itself is subject to quantum jitters. This is why the hunt for primordial gravitational waves is so monumental. They were generated when the universe was small enough for this quantum gravitational chaos to be the dominant force. The specific pattern of these ripples, their amplitude and polarization, is a fossilized imprint of that brief period when gravity was just another quantum force. This makes them our only conceivable way to test the grand theories that attempt to unite gravity and quantum mechanics. Take string theory, for instance. It proposes that the fundamental constituents of reality are not point-like particles, but tiny, vibrating strings. The specific vibrational modes of these strings determine every particle and force, including the graviton, the hypothetical quantum carrier of gravity. The gravitational wave background predicted by certain string cosmologies carries a unique, non-Gaussian signature, a distinct clumpiness that would be the smoking gun for these fundamental vibrations. Or consider loop quantum gravity, which suggests that space-time itself is woven from a network of discrete, finite loops. This theory predicts a fundamental granularity to reality, a smallest possible unit of space. As primordial gravitational waves propagated through this pixelated background, their highest frequencies would have been subtly dampened, leaving a telltale roll-off in the spectrum we might detect. Finding that specific cutoff would be direct evidence that space is not smooth, but built from tiny quantum threads. Every other window into this Planck epoch is permanently closed to us. No particle accelerator will ever reach the required energies, and no telescope will ever see past the opacity of the early universe. These gravitational ripples are our one and only time capsule, carrying data from a time when the laws of physics as we know them were being forged. To detect them is to finally read the first page of the cosmic ledger, written in the language of quantum gravity itself. This faint hum of gravitational waves is not meant to be heard in isolation. We stand at the dawn of a new era in cosmology, one defined by multi-messenger astronomy, where we will learn to see with new eyes and hear with new ears. For centuries, astronomy meant studying light, from the visible colors of stars to the invisible gamma rays and radio waves. Now we are adding new, fundamental messengers to our toolkit. Gravitational waves are one, but we also detect ghostly neutrinos that pass through the Earth almost unnoticed. And we trace the origins of ultra-high-energy cosmic rays that bombard our atmosphere. Each messenger carries a unique piece of the story, blind to different aspects of reality, but together forming a complete picture. Imagine a primordial gravitational wave signal, a specific tremor we finally detect. On its own, it is a monumental discovery, but its true power is unlocked when we cross-reference it with the oldest light in the universe. If that same tremor left a matching, faint pattern in the polarization of the cosmic microwave background, the confirmation would be undeniable. We would have two completely independent witnesses to the same event, one a vibration in space-time, the other a twist in ancient light, both pointing to the same cosmic genesis. This cross-confirmation would tell us not just that the event happened, but exactly when it happened and with what incredible energy. We could then look even further, to the large-scale structure of the universe itself, the vast cosmic web of galaxies and voids. The same quantum seeds that grew into this web also created the gravitational waves. By comparing the statistical patterns in the galaxy distribution to the spectrum of the gravitational wave background, we would see if they tell the same story. Do the ripples in space and the distribution of matter share the same origin? A multi-messenger approach allows us to ask this question directly, building a coherent, multi-dimensional narrative of creation. This is the future, a symphony of data where gravitational waves provide the deep bass rhythm, light paints the detailed melody, and neutrinos add their own elusive harmony. By listening to every channel of this cosmic broadcast, we will move from a collection of intriguing theories to a single, unified, and undeniable story of our beginning. Detecting these first tremors would bring us to the very precipice of meaning. This is not merely another scientific discovery. It is as close as humanity can ever come to witnessing the moment of creation itself, a frontier where the hard lines of physics begin to dissolve into the profound questions of metaphysics. We are peering into an epoch where our most fundamental concepts break down. Consider the nature of time. Our entire existence is built on a clear arrow of time, a relentless flow from past to future. But these ripples emerge from a realm where that arrow may not have yet begun to point. If the no-boundary proposal is correct, time itself may have smoothly transitioned from a state akin to a dimension of space. What does causality, the rule that every effect must have a cause, mean in a domain where time has no clear beginning? The search for a first cause, a philosophical quest for millennia, is fundamentally challenged if the universe has no temporal edge. Then there is the haunting question of nothingness. The universe, we find, did not simply appear from a void. The very existence of these primordial ripples tells us that the nascent cosmos was a seething quantum plenum, a something pregnant with potential. The concept of true nothingness, of a perfect and featureless void, may be a physical impossibility. Instead, the universe seems to have erupted into being with a structure already imprinted upon it, a cosmic DNA coded in those first quantum fluctuations. This quantum breath, amplified to a cosmic scale, determined the location of every galaxy, star, and planet that would ever form. It suggests a reality where randomness and law are intertwined from the very first instant, that the grand tapestry of existence was woven from threads of inherent uncertainty. To finally hear this echo is to confront the stunning possibility that our vast, ordered cosmos is the magnified expression of a fundamental, quantum randomness, a whisper that contains the blueprint for everything. The next generation of observatories is already taking shape, designed to listen for whispers we can barely even conceive of today. On the ground, the successors to LIGO are being planned, instruments of almost unbelievable scale and precision. The Cosmic Explorer is a proposed American observatory that would feature laser arms 40 kilometers long, 10 times the length of LIGO current components. This colossal size alone would boost its sensitivity by an order of magnitude, allowing it to hear the faintest chirps from the most distant black hole mergers, events that are currently just below the threshold of perception. Across the Atlantic, the Einstein telescope, envisioned deep underground in Europe to escape seismic noise, would employ a triangular configuration of 3 separate 10-kilometer arms. This design, combined with its quiet subterranean location, would give it a sensitivity that could detect gravitational waves from the very first stars and their cataclysmic deaths, peering back to the cosmic dawn. These ground-based behemoths will not just find more sources. They will listen with such clarity that they can precisely measure the properties of space-time itself around these colossal objects, testing Einstein's theory in the most extreme environments nature can provide. Our view of the ancient sky is also set for a revolutionary leap. The cosmic microwave background has been our most valuable window into the infant universe, thanks to missions like Planck. But the next generation of CMB satellites will be far more powerful, designed with one primary goal: to find the definitive, curling signature of primordial gravitational waves. These future observatories will carry arrays of polarization-sensitive detectors so vast and so sensitive that they can map the entire sky with a resolution and clarity we can only dream of now. They will be able to isolate the faint B-mode polarization pattern from the foreground of galactic dust with absolute certainty, finally answering the question that has driven cosmologists for decades. Did inflation leave its mark on the oldest light in the universe? A clear detection would be a landmark in human history, a direct observation of the universe's quantum gravitational origins. Beyond even LISA, concepts are being drawn for space-based interferometers of staggering ambition. Imagine a fleet of spacecraft forming a laser network with arms spanning the entire inner solar system. Such an observatory would be tuned to frequencies even lower than LISA can access, frequencies that are the natural domain of the primordial gravitational wave background from inflation and cosmic strings. This would not be merely detecting a hum, it would be mapping it. It could, in theory, create a detailed spectrum of this background, measuring its strength across a wide range of frequencies. The shape of that spectrum would be the ultimate cosmic barcode, allowing us to discriminate between the 30 theories with forensic precision. Is the signal loud and robust, pointing to a violent, action-driven birth? Does it have the specific harmonic signature of a universe crisscrossed by cosmic strings? Or is it a faint, almost silent whisper, confirming a no-boundary quantum genesis or a warm, syrupy inflation? These future machines would move us from simply confirming the existence of the first ripples to reading the fine print of their message, translating the vibration of creation into a detailed story of how, and perhaps even why, our universe came to be. The hunt is accelerating, and the tools we are building will soon give us ears sensitive enough to hear the very first breath of reality. That deep, cosmic hum is not just a metaphor, it is a vibration you can actually hear. Scientists use a process called sonification to translate the raw data of gravitational waves into sound, giving us a new way to listen to the universe. Imagine taking the faint, digital signals from an observatory like LIGO and shifting their frequency upward into the range of human hearing. The result is not a literal recording, but a powerful auditory representation of space-time itself ringing like a bell. Now, apply that to the primordial gravitational wave background. If we could tune our instruments to that ancient static, what would we hear? The simplest prediction from standard inflation might manifest as a deep, constant hiss, a smooth and uniform hum, the residual heat from the Big Bang's own quantum jitters. But the true chorus would be far more complex. Listen closely, and you might pick out sharper, staccato chirps popping against that background hum. The birth cries of primordial black holes forming and colliding in the universe's first second. A persistent harmonic drone woven throughout could be the unmistakable signature of cosmic strings, those infinite vibrating filaments still whipping through the cosmos. The sound might even carry a distinct spin, a chiral quality where the waves seem to spiral in one dominant direction, a clear fingerprint of an action field guiding inflation. This is not merely a scientific exercise, it is a fundamental shift in perception. By turning data into sound, we engage a different part of our mind, one that is exceptionally good at picking out patterns and harmonies from noise. We are not just calculating the universe, we are learning to hear its voice. The first whisper of reality might reach us not as a number on a screen, but as a note in a symphony, a single tone that contains the blueprint for all of existence. From the thunderous burst of inflation to the silent collision of cosmic brains, we have journeyed across 30 possible beginnings. We have traced the echoes of vibrating strings, the scars of cosmic defects, and the possibility that our entire reality is a magnificent hologram. This grand tapestry of theories, each with its own unique fingerprint, is not a sign of confusion, but a testament to the incredible creativity of the human mind, reaching for the ultimate answer. The hunt for these first ripples is far more than a technical challenge. It is our most direct line back to the universe's infancy, a chance to witness the moment when time itself may have begun. The greatest experiments ever conceived are now tuning their instruments, from colossal laser arrays in space to silent telescopes in the desert, all straining to hear that faint primordial hum. Stay with this story. Follow the announcements from these observatories, for the day they report a detection will rewrite every textbook. We stand at the edge of a new sense, on the verge of listening to the very first sounds of the cosmos, the vibrations that set the stage for every star, every planet, and every